Hey friends, welcome to this episode of 10 Laws Podcast with East Forest. I'm Mr. Forest. Thanks for joining us this week. You might have noticed that the cadence of these podcasts has been bi-monthly or perhaps a little less regular than once a week, as it was for almost 5-6 years. Part of that was putting so much time into the completion of the Music for Mushrooms film, and part of that is sort of figuring out, what to do. I don't know. Do you feel like you've been punched in the face and sort of like since maybe the election or something like that, and you're just the world's changing, and it's like our sense of relevancy and meaning, and it's always important to me to not just be parroting myself and to be meeting the moment in a way that feels right and true for you, for me, for this whole picture. So we're not just doing it to do it. And I love having the conversations I have on this podcast. It's been amazing. And I'm continuing to do it. I'm just sort of taking my time not just to press forward full steam for the sake of pressing forward full steam. That's part of a holistic picture for myself, too. These are things that I've been kind of pondering over the solstice and into the holidays, and that's where we are. But today I have a really wonderful conversation with Dr. Will Kinney. He is a professor at the University of Buffalo, Department of Physics. Yeah, so, I'm not exactly a physician. Is that what they call physics people? I'm kidding. But I love cosmology, and I talked to him about that. And Tiffany from Bright Antenna, the record label, she's like, you guys should talk. And so I reached out, and this was a while back, so I'm happy that I'm finally able to get this conversation out. And I feel like the cosmos and the inner space, as above, so below, part and parcel. It makes total sense to me about how it's relevant, and I frankly wish I could talk to more folks like this and have more conversations just to understand things that are far beyond anything I've ever studied. But I love it. And I think you're going to love this conversation too. A few things to note. You might have noticed that this podcast has disappeared from Spotify. If you're listening to this right now when I release it, hopefully it will come back. I don't know what's going on. I reached out to Spotify and I reached out to my distributor, Simplecast, and basically the response I got, the only thing I could get out of them was like, from Spotify, is like, yeah, your podcast was taken down. And I'm like, well, why? And they won't tell you why. They didn't send an email. Nothing. It just disappeared. And it's not like the podcast is up, like you can search it and they grade out an episode or certain episodes or all of them. It's just gone. And you can imagine that's frustrating because that's 6 years, almost 300 episodes just about coming up on it. And they're all evergreen, or most of them. And so it's sort of like there's a catalog of work there. So I'm trying to file an appeal, but there's actually no actual formal way to do that. And I'm trying. My hope is to get the show back up and all the episodes restored. But you can't even resubmit your show, because it has the same RSS feed. You can't change the name of it. Same thing. Like if I did want to just redo it, it's a new show. Like you lose all your subscribers, you lose any ratings, and like I just said, the catalog, the history of all of those episodes wouldn't be included. So it's important to me that it gets sorted out, especially considering I don't even know what's going on or why they did that. Radha's always like, you've been shadow banned, and maybe, but I hope not, because I believe in people in a bigger way than that. And I went up to see why it wasn't there, and I was trying to update something there's a playlist we have on Spotify of podcast episodes, and the whole thing was just gone. It wasn't even something I could search. So that's been a fun way to start the new year. So we're looking to that. Sorry if you're a Spotify subscriber and that's where you're unable to hear it. For those of us everywhere else, Apple Podcasts and so forth, currently we're still kicking there. The robots haven't decided that I should be off. It is possible. I did a little searching, sleuthing They don't like it when you put music in podcasts, like a lot of it, because then they're like, oh, that's not what podcasts are for. You're supposed to use the main, Spotify side of things for music. And a couple episodes back, I shared with you my live concert from Denver, and it's possible they didn't like that. I think like an adult thing to do would have been to perhaps send me a note, an email being like, hey, we don't want you to do this, or we took down this episode or whatever, not just hitting the delete button on the whole thing with no notice. It's talk about rude. It's strange too, considering that the whole point of these platforms is like we are creating content for them so they have an audience. You'd think they'd be more in collaboration with us. And just to say, the music side of Spotify and the podcast side of Spotify, different departments, different people, completely different entities. And, the music side of Spotify is frankly a big part of my livelihood. And it's important to me, albeit, they pay very, very small amounts of money per stream. I own a good chunk of my music over the years. I was always doing it very DIY, so it's just me putting it out. Distributor takes a chunk of that, and then all the other things. But like, even if you make 30%, 40% of what you're putting out, for every dollar, that's important. It's important. Everything helps keep the lights on and keep the shit moving forward. So I want to be like, hey, Spotify, let's keep it. Let's be a family here. I don't know. I'll keep you updated. I'll let you know how this thing adds up. And before we get into this, I'm supposed to be in Salt Lake City at something called Psychedelics in the Beehive. It's like a festival, multi-day thing on January 24th. I'll be playing a live set there that I'm looking forward to. And the Music for Mushrooms film is currently available to see at musicformushrooms.com, meaning it's streaming, but just till January 6th. That is our current window to watch. It's on a sliding scale starting, I think, at $5, maybe it's $10. It's very affordable, and appreciate everyone who's been able to watch it, or if you want to share it with some family or friends or have a little watch party, this is your time. And we also released something called The Essentials. And that's really like a deep dive into all the interviews from the film and things like meditations with myself and Radha and unreleased music. I actually uploaded to The Essentials my entire new Lovingly album that comes out in mid-February, Valentine's Day. And that is my new long-form journey music, 6 hours, 15 minutes. So that's part of it. There's all sorts of stuff basically for you, tools to journey with and tools to learn. All the extended interviews of the film. So check it out. That's at musicformushrooms.com. It's on a holiday special right now, and that's a great way to support the project and help us pay back our investors, which is a big goal of mine. And I want to thank you for all of your help making that happen. And lastly, thank you to everyone on our council on Patreon, patreon.com/EastForest. I've been able to share a lot of music over there, and that's probably going to now be, if I can't share as much music here, over there is the spot. I just shared my entire live set at Wanderlust that I did in Mexico. I shared the entire improvisational music I played for Radha's yoga class. I'm going to be sharing my live set from the beach down there. I share demos, all sorts of stuff over on the council. We also do a monthly Zoom council meeting and more. It's a great way to support the project, great way to dive into the community. And if you love the music or you love music in general, it's my main platform to share all the little orphans I have that have nowhere else to live, just over on Patreon, patreon.com/EastForest, and that's where you can dig into that stuff. I hope you are having a happy new year. We'll be digging into seeing how all this unfolds. I'll have lots of new live dates. Get on the newsletter if you're not on it already. And we're just building, continuing, like I said, to figure out how can we meet the moment with the most grace, with the most love? How can I let go of the unfolding, but still step into the creation, still show up with vigor and passion and eyes wide open and heart wide open at a time when things are, like they are, like the time it is. We don't need to explain it. It's just what it is. But I'm looking forward to that, and I'm looking forward to the way we get to do this together. So thank you for your support. Thank you for listening, and we will continue to evolve together. For now, we're getting into this conversation with our new friend, Dr. Will Kinney. Well, you were recommended to me by a dear friend of mine, Tiffany, who runs the record label I released my last record on. Yeah, and she's like, I was down there having lunch with her, and she's like, you should have Dr. Will Kinney on your podcast. I was like, okay. And so I looked you up, and I personally have a deep affinity and love for cosmology, of course, but I have no deep knowledge on it. I took one class in college on astronomy, and the only regret I had is it was my senior year, and it was my favorite class. And I was like, if it wasn't for the math, I was like, this would have been my jam. So I really love it. And it's actually the only textbook I kept from college, was 'cause sometimes I like to open up and just like read about the basics.
I teach a gen ed astronomy class, for non-majors quite frequently here at UB, and it's one of my favorite classes to teach because it always, really engages people, and it's fun stuff.
Yeah, I mean, it must be nice to like turn people on to things like the basics, because the basics are like what's amazing about cosmology is like, just the observable universe. We observe it. Like, you're looking at it, right? It's like, it's not a theory in that way. It's just right there. And we're seeing the craziest things out there. And just the basics are profound to comprehend the scale and the scope and the time and the heat and all these things.
Yeah, absolutely. It's, it's it's an interesting thing about astronomy that it's in that way accessible to anybody who just goes out and looks up, right?
Right, right.
And you just have to look up with an increasing degree of sophistication.
Yeah, bigger and bigger mirrors. It's wild too, because I have some land I like to spend time down on southern Utah, which is one of the dark skies parts of our country. And it's also very high elevation. It's 7,200 feet, my spot. And the stars are just unreal. And I think a lot about since the Industrial Revolution, when we basically started lighting up our night, and how that changed us as a people, and the generations move forward, and we maybe lose touch with the stars. How that was fundamental to humanity.
I grew up in the West, and I've actually spent a lot of time down in southern Utah. I went to I got my PhD at University of Colorado in Boulder. And so we used to go out to Moab and, Escalante and stuff pretty frequently. But
that's the spot.
Yeah, and I agree with you. I think that there's something that we have lost in when we collect in cities and light everything up, and you can really no longer see anything but the few brightest stars in the sky. And to go to a really dark sky site and to see the Milky Way, or to have the stars actually be bright enough that they're casting a shadow. Is just remarkable, and it's sad that fewer and fewer people in the modern world experience this.
It is,
because it really is moving. Yeah,
and it's humbling. And I just kind of wonder, like, what level of our human hubris, what role it plays that we aren't humbled by our place in the cosmos. I really do think it was a part of what it meant to be a human being forever. And it's really just been recently that we lost that connection by the power of, like, really another form of light, electricity, and keeping us up at night and looking at screens, looking at a different star in our hand in a way. It changes us.
Yeah, I mean, it makes me think of a quote from Carl Sagan, who was writing about the very famous pale blue dot image, which was a picture of the Earth taken from far out in the solar system. And he wrote that it has been said that astronomy is a humbling and character-building experience, and there's perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world, right? So he's musing on this picture of the Earth, where all you see is a tiny little dot in the background of a larger picture. There's several versions of it. One of the most famous is one that was taken of the Earth from Saturn, and it just looks like a little tiny bit. And you think about the fact that, as Sagan put it, every person who has ever lives on that dot. And so that astronomical perspective is something philosophically, I think, that is good for human beings.
Definitely,
to remember how small we are.
Or have you ever seen one of those posters? It basically has roughly a map of where we are in the Milky Way. And then I remind people, it's like, hey, if you're a Star Trek fan, all of Star Trek took place inside the Milky Way. Like, they never left the Milky Way.
Right.
It's that big.
And then that's one of just, trillions of other galaxies like that. And I don't know if you've seen some of the more modern maps that have been produced, but one of the really beautiful things that is coming out of cosmology in the 21st century is that they are making the first maps of essentially the entire observable universe.
Hold on. If you think about it, what does that even mean? Because I have a lot of questions about this, and I tried to get into a bit of your ideas of inflation, and I do have some questions. But when we talk about the observable universe, how do we know that what we're seeing, the furthest we can see, 13.8 billion years of light, that there isn't more?
Oh, well, there probably is, right? So the basic picture of the Big Bang cosmology is you have essentially an infinitely large universe, right? Spatially infinite. But we can only see a tiny little patch of that infinity because of the fact that the universe has a finite age, right? And since light travels at a finite speed, there's only a certain distance that it's possible for light to have traveled since the Big Bang.
Right.
And as you look out in space, you look back in time. So when you're looking at things further and further away, you're seeing them earlier and earlier in time.
Right.
And eventually you run out of time because the universe, in fact, had a beginning, right? And so you only see this tiny little patch of the universe because of the fact that the universe has a finite age. But there's more stuff outside of that, almost certainly, right, that we can't see because we haven't been around for long enough for that light from those things to get to us yet.
And I want to talk about that. But let me just start by asking you this question. I've said this before. It's one of my favorite quotes of Terence McKenna. He's a psychedelic philosopher, heyday in the 80s and 90s. And
I know the name, yeah.
Yeah. He had this great line about, he's like, look, science is sort of posited on this one miracle. He's like, if you can just give us one miracle, that everything came out of nothing for no reason, and we'll run with it. We're cool. And then we can go from there and we'll make all the laws in math. But it is hard for us to wrap our head around singularities in a sense. And even the idea of infinity, like infinity is a thing in math, but I don't know if we've ever it's like more of an idea in the physical universe as far as I understand it. It's what does that even technically mean that it goes on forever or that the universe has an outside or there's more past it in a way to infinity?
Yeah, in a sense that's the simplest kind of. There are many different ways that one could construct what you might think of as a multiverse, right? And the simplest kind is that the universe is just really big. We only see a tiny little bit of it, and there's other observable universes out there that are probably pretty much like the one we live in, except they're different galaxies with different planets and so on. We don't really know that the universe goes on forever. That's a mathematical idealization, right? So we plug in these mathematical solutions, and they're infinite. But we don't really know. All we know is it's a lot bigger than what we can see. And so, and this gets to some of the themes that I wrote in my book, which is, the idea that there are these places in the universe that we in principle, can't see. And so at what point do you stop doing science and start doing philosophy, right? Because science is grounded in observation.
That is so beautiful, because to me, I just think about art. It's like, in many ways, like art and metaphor are the only ways to explain the non-dual or the inexplicable. And in some way, going from math to philosophy, it's like, to me, it's like, that's the boundary condition in a sense.
Yeah, and the boundary between the two is a little fuzzy. And one of the appeals of cosmology is that you have to cope with that. You have to live in these sort of gray areas between, and you end up having to be very careful to delineate where you're standing in terms of science versus philosophy, and it can be very difficult to do. And a lot of cosmologists will disagree on where that line is and what it and where is the right place to stand on that.
So can you tell us a bit about your this notion of inflation? Because like you said, I think a lot of us have learned the basics about the Big Bang, which is some wild shit. I mean, I remember there was a test question. It was essentially like explain the first second of the Big Bang, and I had memorized it. But you're basically talking about things at 10 to the minus 13 seconds. The speed and the scale at which things theoretically expanded. And the idea of that much mass in something the size, well, I guess infinitely small, but even just like a grapefruit, it's crazy when you actually learn about what happened and how quickly. But we all have kind of heard the basic idea, right?
Yeah, I mean, this is really, it's one of the sort of the most consequential ideas of 20th century science, I think, this idea that the universe had a beginning.
Well, I mean, did it?
Because prior to that, I mean, if you look in like the late 19th and even into the early 20th century, it was still very much a matter of dogma that the universe was essentially static in time, that it existed forever and was pretty much the same through all time. And even up into the early 20th century, people believed that the entire universe was just our galaxy, right? It was called the grindstone universe. The belief was that we just lived in this disk of stars, and there was nothing but sort of infinite empty space outside of that. And it wasn't until up in the 1920s that it was realized that this model was wrong and that there were other galaxies and so on. And also with the development of Einstein's theory of gravity, then it was realized that the idea of the Big Bang came into place, this idea that the universe came out of an initial singular point, a mathematical point where everything goes to infinity. Inflation is something that came along in the late 20th century. In the 1980s was the first, was when Alan Guth wrote the first papers on this. And it's really a theory of what happened before the Big Bang. Right. So we think of the hot Big Bang, the standard picture of the universe is that in the early universe, because of it, the universe is expanding. So if you turn that around backwards, everything gets crammed together. So the early universe was very dense and very hot. So it
like
was
a big
primordial
crunch.
Exactly. Just looking at time backwards, the expanding universe, you run the film backwards. You have this universe where everything was closer together at early times. And so you would have had this very hot, dense superparticles that was sort of the initial state of the universe. So you got to ask the question, and that sort of brings up the question, where does that come from? And inflation is an idea that about what happened to create that initial hot, dense state of the Big Bang itself. So instead of this coming out of this singular point, which is in a standard Big Bang theory, that if you just follow this back, you get to a mathematical singularity. The density goes to infinity, all of your math breaks down, and you don't know what's going on. Inflation replaces that point at which your math breaks down by the end of an earlier epoch that was very, very different. It was not hot. It was not dense. In fact, it was very cold. It was at absolute zero, and the universe was completely empty. And the only thing that was in it was an energy that was associated with space itself. So you have an empty, absolute zero universe that where space itself has energy. And this creates this incredibly rapid expansion. So you take a tiny little patch and stretch it out to enormous scales. And a hot Big Bang, that moment at which our universe is created, is the end of this inflationary period where that energy of the vacuum turns into all of the particles that make up us.
Oh, look, I'm a big dummy here. Wrap my head around this. You're saying that in the prior epoch, there's nothing.
That's right.
And in
literally
this
nothing.
plenum of nothing, it sounds like you're saying suddenly everything came out of that and turned into the Big Bang.
That's right. That's one way to.
How is that different than us being like everything came from nothing for no reason, and then we'll run with it? Or is it the same idea?
Well, except that you can write this down, right? So I can write down one of the really beautiful things here is that because the energies and the energies involved are so high and the times involved are so small, that the physics that's relevant is to describe the state of the very early universe is you need to use particle physics to describe it. So the stuff we study at the big particle colliders, like the Large Hadron Collider in Switzerland, right? And so you can write down a particle physics theory that will actually produce this behavior, and you can actually calculate things. And one of the beautiful features of this is that the universe right now is all full of structure, right? It's clumpy. Planets, and we have planets and stars and galaxies and clusters of galaxies and so on. All of that structure in the universe, the way matter is clumped together, was created from gravity out of very, very tiny little fluctuations in the density of the universe at early times. So the very early universe was very smooth, but it had tiny little imperfections in it. And then through the action of gravity, all those imperfections turned into all the structure we see today. But then you ask the question, what created those tiny imperfections? And in inflationary theory, those imperfections were created by quantum effects during this earlier epoch before the Big Bang, when the universe was dominated by essentially the energy of vacuum. And quantum mechanics produces these fluctuations that then collapse to form all the structure. And you can actually calculate what those little imperfections would look like and compare them to what we see in the universe, and you can do real science. So
I'll take your word for that. Yeah.
yeah, and it's a beautiful calculation. And so the point being that you can actually write down specific theories of how this would work. Not only that, but you can write those theories actually make testable predictions, and you can go out and do science with them.
But the testing would be like the Higgs boson, or is this how you're trying to prove that or see it?
Well, for example, you can look at the way galaxies are distributed in the present universe.
Okay.
And then you can infer what initial conditions would be required for that, and then and so that if the particle physics behind inflation worked a little differently, galaxies would be distributed a little bit differently, and you would be able to tell the difference. And also, one of the most powerful probes of this is looking at the leftover light from the Big Bang itself, which is called the cosmic microwave background. So when the universe cooled at about, so it started out very hot and got cooler and cooler, about a little less than 400,000 years after the Big Bang, the glow, the light from that hot early universe was released and is still present today. It's just cooled off and it's now at a very low temperature, but you can detect that. And what you're really remember looking out in space is looking back in time. And when you're looking at this light called the cosmic microwave background, you're actually looking at photons that have been traveling to us since the universe was only about 400,000 years old. And so you can actually see what the universe looked like 380,000 years after the Big Bang. We can directly observe this. And so you can see those initial imperfections that later collapse to form structure, but you can actually see them in their primordial form by looking at this leftover light from the Big Bang. And this is a very powerful test of these theories of inflation about what happened before.
Well, why is it then that some people are not on board with a theory of inflation if it's testable and observable?
So inflation makes a number of pretty specific predictions. Some of them have been confirmed and others have yet to be confirmed. Like one of the big ones is that you should also produce ripples in the space-time itself called gravitational waves. And we have yet to find those. So far, they're too small for us to detect. And there are some theorists who have proposed alternatives that produce similar predictions, but through different mechanisms. For example, the universe going through a bounce where it contracts, reaches a minimum size, and then re-expands again.
That's what I want to ask you about.
Yeah.
Now, am I remembering this correctly? The Hubble constant has to do with whether we're expanding or not the universe?
Right. Yeah. So okay. the Hubble constant is a measure of how fast the universe is expanding.
So what is the current consensus? Are we expanding or slowing down? Where are we at with that?
As far as we know, we're definitely expanding. That's been known since the 1920s. And the thing that is a more recent discovery is that what people expected was that the universe is expanding, but everything in the universe is pulling on each other, everything else with gravity, right? So you'd expect that mutual gravitational attraction to slow that expansion down.
Yes.
And in the late 1990s, this was what everybody expected. And they went and and two different groups went to measure this slowing down of the expansion called deceleration. And what they found was that instead of the expansion slowing down, they discovered that the opposite was happening. It was actually speeding up.
Well, I was kind of hoping it would be nice, it would be elegant if essentially there's an in-breath and an out-breath. It almost aligns with Vedic philosophy in a sense. It's like where it explodes and then eventually it goes the other way and then this just continues over time.
These cycles of existence,
but right? I kind of hear that from you with inflation in a sense. Like in a sense, it's just a more complex way of looking at cycles or infinite cycles.
Well, yeah, maybe, but not really, because people have come up with models where the universe actually does go through cycles. And inflation is fundamentally different from that, in that instead, what happens is the inflationary universe is you expanding incredibly quickly. And so I was saying before that our universe is the end product of this, where this energy of empty space that was driving inflation decayed and turned into all the particles in our universe. Well, the interesting thing is that when you actually write down a theory of how this happens, a definite theory, you find that not only does this happen in our universe, but it happens multiple times, that inflation keeps going on forever and only ends in little bubbles. And then it creates more of these bubbles and so on. And in fact, what happens in this inflationary universe is it generates an infinite number of universes forever into the future. And so we're just one. So our universe, which is itself spatially infinite, is one of an infinite number of copies of this that are constantly being produced out of this energy of empty space. So somewhere very, very far out there, far beyond what we can see, there's other universes being born as we speak, and this process goes on forever.
Let me ask you
but
about.
That's not a cycle so much, right?
Right,
It's not repetition. It's continuous production.
Okay, let's talk about black holes for a second. Going back to this idea of singularities, and am I correct that we've never actually seen a black hole? We only see the effects of black holes.
We have, at this point, there is a project called the Event Horizon Telescope that has produced, and it's a network of radio telescopes. So they use radio telescopes all over the planet, combine them together, and they've actually produced images of the black holes, these supermassive black holes at the centers of galaxies. Right. And so you can actually see the matter that's falling into the black hole, and you can see the big black spot at the center, which is where the black hole is. And so you can't image a black hole itself because it's black, right? It doesn't by nature, it doesn't give off any radiation, but you can see the place where it is.
Okay. So if mathematically that is a singularity in there, and we don't know what goes on when you enter into the black hole, at least, we have theories. Right. Is it possible that that on the other side of that, in a way, or that is how we're producing more big bangs in a way, like an infinitely dense place of mass? Or could it be that they're all over the place? We've got one in our galaxy. I mean, they're all over, these black holes.
Pretty much every galaxy has a supermassive black hole at the center of it.
And they're formed from exploding stars, right?
These big ones, we don't know how they're formed.
Some are explored.
We know that black holes do form from exploding stars, that they're the leftovers of supernovae. Those are, 5-10 solar mass objects.
Black dots. Yeah.
Yeah.
There's more and more of them. I mean, we're constant stars, in theory, as time goes on, there's just more. And I'm just wondering if that's...
So we know those exist. But the big ones at the centers of galaxies, these are anywhere between a few million and about 10 billion solar masses. And there is, one thing we know is that there's just not enough time in the age of the universe for these little ones that are made in supernovae to coalesce and to form these big ones. The math doesn't work. So there must be some other way that these are forming, and it's not really entirely well known where the hell they come from, but they are everywhere. Every spiral galaxy has one. The one inside the Milky Way is a little one. It's only about 3.7 million solar masses.
Thank God. It would be sucked right in. Yeah.
But other galaxies have ones that are hundreds of times or thousands of times as big. And these, like a 10 billion solar mass black hole, would be large enough to contain essentially the entire solar system inside its horizon.
That's crazy.
Yeah. These are enormous things. And we really don't know where they come from. But yeah, as far as what's inside them, there have been people who have written down theories where you could actually, the interior of a black hole would then be connected and it would expand outward into an inflationary universe through the interior.
Right.
Alan Guth wrote some papers about this. The fun part of that is that it opens up the possibility that one could actually artificially create new universes in a lab.
It sounds like that's one of those experiments, like when they were doing the original atomic experience, like some people are like, this might end the universe. What if we all get sucked in instantly and that's that, that'd be the ultimate whoops.
So you probably don't want to create black holes in the lab.
Probably not.
But the point is we really don't know what goes on inside them because we're separated by a horizon. This is a weird fact of Einstein's theory of gravity, is that in some ways it contains the ingredients of its own demise, in that Einstein's theory predicts that these singularities are going to be there, right? And one kind of singularity is at the center of a black hole, where the stuff that collapses into it just continues to collapse and eventually just disappears into a mathematically infinitely small point. Now, once again, this is an artifact of the mathematics. In reality, we really don't know what happens because our understanding of the physics is breaking down. And presumably what people assume is that there's some sort of new physics is going to come into play that's going to regulate that infinity. One way to think of this is imagine you're sharpening a needle, right? So you take a piece of metal and you sharpen it down to a finer and finer point. And if you think of the metal as just being a continuous material, right, that you could sharpen that point infinitely sharp. Right, you could get that down smaller and smaller and smaller. In reality, what happens is eventually, once you get that tip small enough, you have to care about the fact that the metal's made out of atoms. It's not continuous. It's actually made up of a bunch of little balls that are all stuck together.
Ultimately, space, just empty space.
And so you can't sharpen that tip down to be smaller than the size of an atom, right? Because it's made out of these little fundamental building blocks, right? So that this idea that you could infinitely sharpen a needle breaks down because of the fact that new physics comes into play because it's made out of atoms. The idea is that something similar would be happening at the center of a black hole, that space itself is in some way discrete so that you can't cram everything down to an infinitely small point, that some new physics, presumably related to the quantum mechanics, comes into play. So this is where people talk about string theory and quantum gravity and so on.
Wasn't fractal math developed to like answer the question of measuring a coastline? Like the more you zoom in, it gets more.
That's right.
Yeah. It's a similar idea of like, well, the more you go in, and with the fractal math, it's infinite. It's just an infinite zoom.
That's right. And of course, with a real coastline, eventually you get down to what you'd be seeing the individual atoms, and it would cease to be fractal, right?
Yes. But then we get into the quantum space, and as you know, it's the spooky space. And I thought that was the new physics. If we're talking about a new physics, here's one of my questions that have always confused me. The Higgs boson that they're searching for, it seems to be they always want to build a larger and larger collider to do this. And they're looking for something smaller and smaller every time they do it. And if I remember correctly, when they quote unquote found evidence of the Higgs boson, it wasn't seeing the actual Higgs boson. It was sort of like things that point to it, or it's like there's a relationship.
You see in the decay products. That's right.
Yeah.
So the Higgs boson itself has such a short lifetime that you can't like make one and put it in a bottle, right? It immediately decays into other particles. So what you do is you look for the particles that it decays into and then trace that back and say, aha, these had to have come from a Higgs boson. That was sort of that definitive evidence for the existence of the Higgs happened about 10 years ago, a little bit, about 12 years ago now.
Wouldn't it be reason to think that there'll then just be something smaller after that, and that goes in infinity? And conversely, like every time we look on the other end of the spectrum, like when Hubble looked at the most boring, darkest part of the sky, of course, what do we see? Unbelievable amounts of more galaxies. It's like maybe there's a lesson here about it's like it just never ends.
Yeah, well, I mean, particle physicists don't know the answer. The assumption is that there are reasons that we believe that the standard model of particle physics, right, the Higgs boson and the quarks and so on, we have a very good model that explains what we see in colliders. And it's very well developed, and you can do very detailed calculations of this, of all these processes. And it works. It matches the experiments incredibly well. It's extraordinarily well tested at this point. But there's reasons that we believe that it's incomplete, that there's more to the story. One of them is the existence of dark matter. It turns out that all the particles in the standard model, if you add them all up and you figure out how much of the universe they make up, it makes up only about 4% of the stuff that's out there. The other 96%, we don't know what it is.
That's a big number.
Yeah, 96. I know. It's sort of embarrassing, isn't
like
it?
In a class, that's like, you aced it. You got it all. 4% is not like, hey, we understand most things. It's like, wow, 96%. We can't see it. We can't account for it. We don't know what it is, but
we know it's there because of the way it gravitates. We see it.
But we know it's there. That's why I'm like, how do you know? Yeah. I gotta say, that's pretty wild.
And so this is one of the motives to build bigger colliders is that understanding this dark matter might require physics at higher energies than we've been able to test so far. So the idea is that if there are particles that are heavier than the Higgs or the top quark or whatever, you need a bigger collider to produce those heavy particles, right? This is just E is equal to mc squared. If the mass is big, you need a big energy to make that mass, right?
Very, very, very big energy, yeah.
Right. And so the higher the energy, the more massive particles you can produce. And so the idea is that if this dark matter, for example, that we can see because of its gravity, but isn't accounted for by the standard model, if this is some heavier particle, we might be able to produce it in larger accelerators. This is the hope.
Do you think, aside from physical experiments, AI could bring any meaningful new revelations to cosmology?
AI is starting to be used in both particle physics and cosmology to understand extremely large data sets. And this is so AI, I don't see AI as being so much of a tool for theorists in the sense of coming up with a unified field theory or something like that by asking a computer to do it. Where it's useful is understanding large quantities of data. And one of the very exciting things that's happening in astronomy right now, traditional astronomy worked along the lines of you got a telescope, you pointed it at something, and you looked at that thing like Jupiter or the Andromeda Galaxy or a quasar or whatever, right? And this is the way astronomy has been done for thousands of years. Before the invention of the telescope, it was done with the naked eye and so on. But what we're doing now is what are called survey instruments. So very big telescopes. One of them is called the Vera-Rubin telescope, which is under construction. It's about to start operation. And there are some smaller scale experiments that have already been running. For example, they're called the Sloan Digital Sky Survey and DESI and so on. The idea of these is very different. Basically, you're just pointing a telescope at the whole sky. And you're doing that over and over and over again. So the Rubin telescope will image the entire sky that's available to it. So it'll miss. It's in the southern hemisphere, so it'll miss a bit of the northern
That's
sky.
the one that's the world's biggest camera. That's going to just photograph everything for a while, and they had this unbelievable megapixel situation.
That's right. It's
a 3D
like
image of
And they just finished building this at Stanford and have shipped it down to Chile to install. But this telescope will be capable of imaging the entire sky at extremely high sensitivity every 3 days. It will just take a picture of the sky every 3 days for 5 years, and it will just observe everything. And now the question is, how do you make sense out of that enormous torrent of data, right? This is going to be petabytes of data. And this is one of the places where I think there's a lot of optimism that AI is going to be helpful, because you actually point an AI at this thing and look for it to find patterns that you might have missed. And it's a very exciting time, because I think that every time in astronomy you open a new window on the universe, you discover something you never expected to see. I don't see any reason to believe that this is going to be any different. And it's going to be very exciting to see what unexpected thing pops out of it.
That image from Hubble of the dark sky they did a while back, that's one of my favorite images.
The ultra deep field, or the Hubble deep field.
Yeah.
Well, this is basically the idea of Rubin LSST is to do that, except on a vastly larger scale. So it's it's going to be a complete game changer. So instead of with Hubble, they took one tiny little patch of sky, opened the shutter for 11 days of exposure, right? And it was a patch where there was almost no foreground objects, right? It was just completely blank, and they got this amazing deep picture of the universe. So now we're going to be doing this with the whole sky over and over and over again every few days for a period of years.
What are we going to do with the fact that they're probably going to start imaging like objects that move or things? So it's like people are going to be like, what do we do with this? Because look, there's been weird things that have happened on NASA missions, and they're not the craziest things in the world, but it's like, what is that? And we just seem to be like, I don't know, let's not go there.
One of the big things that this is going to reveal that previous things weren't sensitive to is transient objects, things that change with time. So either they move or they change brightness with time, or so what you get out of this is time sequences. Exactly. And so we've basically been blind to any time dependent phenomena in the universe up until now. And we're finally creating these instruments that will allow us to probe this other aspect of the universe, right? So the universe isn't static; things are happening in it all the time, and this will give us sensitivity to that, and will open up whole new windows. So who knows what you're going to? One of the sort of just the side effects, one of the byproducts of this is we're going to have this enormous. It's going to create an enormous catalog of solar system objects, asteroids, and tiny, all these
Well, we
little
need to
rocks
know
that are
about
floating.
that. Yeah.
Yeah, we care about whether or not
That's
those things are going
important.
to hit us, right?
They do. Yeah.
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 And so getting a catalog of all of these asteroids is going to be tremendously useful. And that's just sort of a side effect. That's not what the thing is designed for, but it's going to be really good at it.
What do you make of like the Fermi paradox and the idea of whether or not we've been visited or we are in contact of any kind with civilizations that evolved maybe 1 billion years before us, and maybe they travel dimensionally, and that's not with rivets and rockets and.
Yeah, I mean, I don't know. I don't think that there's any actual credible evidence that we have interacted with any extraterrestrial civilizations, that human beings have ever done so. I mean, there's lots of speculation, but I haven't ever seen any evidence that I believe.
What do you make of like these more recent congressional hearings where they look at like the Tic Tac object, like radar of objects that are moving beyond ways we know how to move right now through the physics we know?
Yeah, I suspect that there are perfectly sensible and much more mundane explanations for these things than being extraterrestrial. But one needs to maintain an open mind, just not so open that your brains fall out, and that can be a difficult balance. But
are you interested in that, or is it you feel like it's a sideshow, a distraction?
I haven't really been spending a lot of time following those particular, like those congressional hearings. Once again, there's the evidence is there's some weird stuff, but none of it really is a smoking gun for little green men, right? It's possible. I think it's more likely that it is something of terrestrial origin in these cases. As far as the Fermi paradox itself, right? For your listeners, the idea of the Fermi paradox is that if life is abundant in the universe, and I think that there's every reason to suspect that it is, why would we be unique, right?
Right.
That if life is so abundant in the universe, how come we've never talked and we've never seen any of it, right? We have radio telescopes that are perfectly capable of communicating across interstellar distances, for example.
Take a long time, but yeah.
Yeah, well, physics is physics, right? And the speed of light seems to be a hard speed limit. And that's one thing that certainly is an impediment to traveling through interstellar space, is that you just can't go faster than light. And it's also very, very hard to accelerate things up to even anywhere near the speed of light. It takes a tremendous amount of energy and resources to do that. Unless that physics is wrong, unless there's a loophole in that, actual interstellar travel is likely to be incredibly difficult. But you can send radio signals. And so far we have seen no evidence of any, sort of artificial electromagnetic waves coming from any stars or anything like that. So yeah, why is the universe so quiet if life is abundant? So there are various explanations for this. One is that, maybe civilizations have a very short lifetime before they tend to destroy themselves, right? That's called the Great Filter Theory.
How macabre. Yeah.
Yeah, I know. Well, even more macabre, and the one that I think is most interesting was put forth in the three-body problem. Right, there's the show on Netflix now that came out of Chinese sci-fi
I saw
novel,
that.
right?
I really disliked it, but I watched all of it.
The books are good. I haven't watched.
I could see that. Yeah, I could see that.
But it's by a Chinese science fiction author named Cixin Liu, and in the second book of that series, there's kind of a spoiler here.
Spoiler alert! Spoiler.
Yeah.
Alert.
So it is the dark forest theory, which is the idea that any civilization you run into is likely to be vastly more advanced than you.
Right. Yeah.
And therefore, if you encounter another civilization, the only rational response is genocide. So that the reason that we don't see anybody is because everybody is keeping quiet, because as soon as somebody makes their presence known, all of the more advanced civilizations in the universe come and wipe them out.
And as to play devil's advocate, we could hopefully, I look at human nature as we're these weird animals that are evolving, but we have our ability to have agape consciousness, brotherly love. We have this. We can philosophize about the universe and so forth, or even psychedelic states. And hopefully, I would say our evolution moves into more of like it's not about, we're moving away from our animal tendencies of like just destroy to control, or even just our sort of, since Newton, just our way of operating the world was like, it's all control, controlling explosion and combustion and nature itself. It's how do we work symbiotically as a way of, that is our only way of continuing. Like that's some kind of boundary condition on civilizations. It's like, can we move beyond that notion?
Right. Well, that gets you to the great filter, right? Are we capable as a civilization, capable of creating, living enough in harmony with the universe that we can actually survive beyond a few hundred or a few thousand years as a civilization? And that sort of remains to be seen with humans.
Yeah, this is where we're at. Yeah,
but
we're at that
the
moment.
dark forest theory is even more pessimistic than that, which is that any civilization that operates according to the principles of brotherly love that you espouse would be immediately exterminated.
Unless they're the one that is the ticket for evolution to continue. I mean, who knows? But I mean, we know that just like the odds of life even existing, the Goldilocks idea. I heard someone say that, like, all of this being exactly how it is, like our distance from the sun and all of it, is almost like the equivalent mathematically of taking the parts of a Boeing 747, throwing them in the air over and over again until it falls in the right way that it comes together. Like it's incredibly unlikely.
Physicists have a word for this. It's called fine-tuning, right? So the idea being that things have to be absolutely just so in order for beings like us to exist, right? And one of the favorite things that physicists like to bring up is the strength of the electromagnetic force, right? The force that binds atoms together. And this is determined by a number called the fine structure constant, which is equal to 1 over 137. And we have no idea why this number is equal to 1 over 137. And it's not exactly that. It's a bunch of digits, right? And this is not explained. It's just a number that we measure. And if that number were even slightly different by just a fraction of a percent, then, for example, carbon atoms would no longer be stable and you couldn't build carbon-based molecules and life wouldn't exist, right? So the fact that this number is precisely that value is our existence is contingent on that.
Yeah, that is so wild.
And so one of the things that cosmologists spend a lot of time arguing about is what's the source of that fine tuning? Why are things sort of just so, right? And there are sort of two competing ideas. One is called the anthropic principle, which is the idea that in this like inflationary multiverse, you might have universes where this number was wildly different, but those universes would be deserts. They would be empty of life. And that the reason that we see the constants being what they are is simply a byproduct of the fact that if they weren't, we wouldn't be there to observe them. And this is the anthropic idea. And one of the things that I spend a lot of time on in my book is critically examining this anthropic idea, this idea that the universe is very fine-tuned for life and that we're in some sense special. And this idea is really in conflict with the idea that was first put forward by Nicholas Copernicus, right? The idea of the Copernican principle is that we're not special, is exactly the opposite, that we are in some sense ordinary. And this was really revolutionary, right? If you look back into the Middle Ages with the geocentric universe where the Earth was at the center and the sun and the moon and the planets.
If you said that was different.
Well, in fact, Giordano Bruno was burned at the stake in part for advocating Copernican, a sun-centered universe. But this was this old universe that came from Aristotle and propagated through the Roman Catholic Church and so on, was one in which the laws that govern the motion of celestial bodies or ethereal bodies were completely different than the laws that govern things on Earth, right? That physics was not universal. That material bodies behaved in one way, ethereal or celestial bodies behaved in another way, and there was just two completely different rule books for how they worked. Copernicus really introduced his revolutionary contribution wasn't so much the idea that the sun was at the center of the solar system. That goes all the way back to Democritus in ancient Greece. But what Copernicus realized was that in order to have a heliocentric cosmology, you had to have a universality of physical law, that the laws of physics that worked in the sky were the same as the laws of physics that worked here. And that is a profound shift, right? So this universality of physical law is what makes any kind of a science of astronomy possible, right? Because we can do experiments in the lab here and we can say, oh, that actually still, those laws of physics and electromagnetism and nuclear physics and so on work on the other side of the universe the same way as they do here. And that's a profound shift, right? And this Copernican idea of universality of physical law now gets challenged by this idea that you have a multiverse where the laws are different in all of these different universes, right? An alternative viewpoint is that this universality applies not only within our particular cosmos, but in other universes as well, right? That are being produced by inflation, for example. And in that case, then the fine structure constant probably wouldn't be different in these other universes. It would probably be the same, and they would be teeming with life just like ours. We have no way of knowing for sure. It's largely a philosophical question, but the way you frame your viewpoint on that actually influences how you ask questions about what we can observe as well. So it's not the philosophy there is still useful in the sense of how we ask scientific questions is informed by how we look at these larger philosophical issues as well.
So in your view, is inflation theory sort of the Copernicus of today, or what is?
Yeah, I mean, and so that's what I try to argue, is that really inflation enforces a Copernican viewpoint on a vastly larger scale than we'd ever thought of before, not only within our universe, but between our universe and an infinity of other ones. And this, one of my favorite quotes comes from the Renaissance philosopher Giordano Bruno, who was the guy who was executed by the Inquisition in 1600, in part because he advocated Copernicanism and heliocentric cosmology, but also because he was a guy who took Copernicus's ideas and extended them in a way that even Copernicus wasn't intellectually bold enough to do. Right? He realized that if the Earth isn't special, that means that essentially no place is special. He realized that the other stars would be other solar systems like ours, that would have other worlds like ours on them, that could have other civilizations and so on. And in 1584, he wrote in his book on the infinite universe and worlds, Copernicus wrote, God is infinite, so his universe must be too. He is glorified not in one, but in countless suns, not in a single earth, a single world, but in 1,000,000, I say, in an infinity of worlds, which is, of course, where the title for my book came from, which is An Infinity of Worlds. It's a quote from Bruno. And inflation takes that Bruno's infinity of worlds and extends it even further into an infinity of universes. So I write down a theory that tells me why the universe I live in is so big and why it's so old and why it's so close to geometrically flat, and explains how all the structure arose, and it's a definite theory and I can test it and all of these things, right? So and I can actually look at the first light from the Big Bang and I can compare that to this theory and they match up nicely. I can do all of these very hard-nosed scientific tests that tell me that this theory is well supported by data. But then if I take this theory and just examine its consequences, what I find is that you don't just get one universe out of it, you get an infinite number of universes out of it completely for free.
Free.
Well,
thank God. Otherwise, that'd be an infinite bill. Yeah, that'd be the infinite debt. Yeah.
So in explaining our universe, you inevitably end up with the realization that if this theory is correct, it predicts that ours is just one of an infinite number of them. And so it's a beautiful extension of these, several hundred-year-old Copernican ideas that, and Bruno was way ahead of his time. He had a remarkably modern sensibility about how he looked at these things, so he's sort of one of my scientific heroes because he was very bold.
Bruno.
Yeah.
Yeah, I saw that movie with Sacha Baron Cohen. No, I'm kidding. So let me ask you this. The idea that it's infinite more iterations, and for yourself personally, does that give you comfort, or how does that make you feel? Like, does it create more? Do you feel less significant in your own sense of being in the world and why all this is here?
I guess personally, in terms of philosophically, I find it in many ways reassuring that we're just like sort of essentially not terribly important in the world. a billion years from now, it is unlikely that anyone will even that there will be any indication that our civilization ever existed, right?
Yeah.
And in 5 billion years, the sun is going to expand into a red giant, swallow up Mercury and Venus, and scorch the surface of the Earth, scorch away the oceans and the atmosphere, and there will be nothing left. And that dead cinder of the planet will continue to revolve around the remnant of the sun for eons and eons beyond that. And there will be new life elsewhere in the universe, and it will go on. But that doesn't make me feel bad. It just makes me feel connected in a way that I'm just one little part of the natural processes happening in the world, and I'm a very small part of that. And there are much larger things going on. I don't know if that makes sense to you.
Sure. And I look at Romanesco broccoli. You've seen that in the store ever?
Yeah, the fractal broccoli. Yeah.
Yeah. It's like that kind of sums it up to me in some weird way. And it's like the fact that just grows out of the ground. It's some kind of evidence of like, oh my God, they let the secret out, or
it's the power of mathematics, right? I mean, it's an incredibly mathematical object, and galaxies in the universe are distributed in a fractal pattern as well.
Yes.
So you have structures, larger structures made up of smaller structures, made up of still smaller structures, and this repeats itself. This is a property of dark matter, right? So this is a prediction of these dark matter theories that dark matter is made up of these heavy particles. It predicts this fractal structure to the cosmos that we actually can go out and see. So like the Romanesco broccoli, where you see those worlds within worlds within worlds, that beautiful fractal pattern that looks like a Mandelbrot set or something like that. That's a consequence of the mathematical rules that are underlying the cellular growth of this planet. A consequence of the mathematical rules that govern the clustering of dark matter under gravity produces a similar fractal pattern. And we can see that in these maps we're making of the observable universe, that fractal pattern is becoming evident. And it's very similar. It's just it's a consequence of the math that is written on this huge stage. And it is so beautiful.
Yeah, it really is. I mean, is it true that the sort of like what's happening, that how stars sort of mass up in flocculent arms is similar to the effect of how humans bunch up in traffic?
Yes, right. Those are density waves. So
that's nuts.
Yeah. So if you've ever been on the highway and there's been a wreck and they've cleared it, but the traffic jam is still there because the cars are slowing down, and then the ones behind them slow down, and by the time they speed up, more cars have come in. So you get this standing wave that's sitting there, but there's no obstruction left. It's just a dynamical artifact of the fact that there was something there an hour before, right? We've all seen this in traffic jams. That's exactly the process that creates spiral arms. Is that like a cloud is not a thing. A cloud is a process, right? That things are moving through it, and you're only seeing the pattern of condensation that happens because of the temperature differentials. Or this backup in traffic it's not all the same cars. New cars are moving in and old ones are moving out, and so that traffic jam is a process. The spiral arms in a galaxy are very similar in that sense, that they're these density waves. And what happens is when the gas crashes into these overdense regions, this traffic jam, it sets off star formation. And the reason that we see those spiral arms as being bright is because they're full of bright young stars, right? I mean, you look at the sky, right? And what do you see? If you go out, back to what we were initially talking about, right? So if you go out at night and you look up at the sky, what do you see?
A lot of stars.
Stars, right.
And
so
a couple
why?
planets, but yeah, a lot of stars.
Why do you see stars?
Because our eyes can, the photons from those stars took many, 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 many years, and they go right in my eye.
Right. Yeah. But if we saw a different wavelength of photons, we wouldn't see stars at all. We'd see gas clouds if we saw in the deep infrared, right?
Right.
So the reason we see stars is evolution. Is that our eyes evolved to be sensitive to starlight because because we live next to a star, and that's where most of the light comes from. So we see in a very narrow wave band that is where the sunlight peaks because of the temperature of the sun, and so our eyes are optimized to see stars because the world is flooded with starlight. If we saw in different wavelengths, we would see the universe would look completely different to us. We wouldn't see stars at all. We would, for example, see if we saw in the infrared, we would see grains of dust in these huge clouds. If we saw in the microwave, we would actually, if we saw on the right frequencies of microwave, we would actually see the brightest thing in the universe is the light from the Big Bang, the cosmic microwave background. And so because our eyes are tuned by evolution to a particular wavelength, we see stars when we look at the universe, but that's an accident of biology. And in fact, if you well, presumably, I don't know. Are there beings that evolved in other places, right, where there wasn't so much starlight available, right? And they would see the universe very differently from us.
Well, speaking of what we can see, last couple questions. What do you think is the promise of James Webb, this new telescope? Speaking of being able to see things, it's new.
Yeah, and so it is uniquely powerful in terms of its ability to probe further out in space and sort of further back in time. And one of the big questions that is outstanding in cosmology right now that people really want to understand better is, how did the first stars in the universe light up, right? There was a first star that formed inside our observable universe, right? So after the Big Bang happened and this primordial soup cooled down and turned into just like clouds of hydrogen and helium gas, but there were no stars yet, right? So the universe was cooled off and it's just big clouds of hydrogen and helium and nothing else. And this is called the Dark Ages. So this is from starting when the universe was about 400,000 years old up to when it was a few 100 million years old. There weren't any stars and there was no starlight in the universe. It would have been completely dark to our eyes. And then gradually, as these clouds of gas collapsed, they started to form the first stars that formed in the universe. And those, we are pretty sure those stars are very different from current stars, because current stars have heavier elements mixed in, carbon, oxygen, things like that. And there was no carbon or oxygen or anything in the early universe. So these first stars lit up and then exploded into supernovae and populated the universe with heavy elements that eventually turned into us. And very little is known about this first generation of stars because we've never seen them, because the telescopes we have aren't powerful enough to look out far enough to see these very early stars and galaxies forming. And for a cosmologist, this is one of the things that the James Webb Telescope is going to be really useful for, is it's going to start probing the end of the Dark Ages, when the very first stars lit up and the universe first became light. And it's a very mysterious time in the history of the universe, and we don't know a whole lot about it. And it's going to be very exciting to see Webb especially. And there are already surprises coming out.
Yeah.
Webb is finding that early galaxies were much larger and better organized than we expected them to be based on our theories of dark matter. And so we might have to modify some of our ideas in order to accommodate this. It's still early days, though, and it's not really well understood exactly what the significance is.
And what is the significance or purpose of understanding these things for here on Earth? People might say, like, look, we got some serious problems here. Why do we need to know what happened 13 billion years ago?
The only answer I have to that is people have always wanted to know where we come from, right? And I mean, for most of human history, that's the province of religion. Every culture has a creation myth, what created the universe, what created humanity, what created everything we see around us, right? It's a universal human curiosity. We care about this. And cosmology is the science of this, right? It's taking those questions of human origins and cosmic origins and placing them on a sound scientific footing and actually coming up with real answers to these questions. And to me, that's tremendously exciting. And it's, that is an ancient human imperative, is to understand our origins. And it's thrilling to be able to work as a scientist to actually come to an understanding of these things, even though it is ultimately going to be imperfect and partial.
Yeah.
Yeah.
Isn't it wild that like the Mayans could figure out the precession of the equinoxes by just, I guess, looking at the stars?
Yeah, well, not just the Mayans, but the ancient Babylonians were remarkably sophisticated astronomers 4,000 or 5,000 years ago, and they understood, for example, the precession of the equinoxes and all of these things, and the Mayan calendars were quite sophisticated as well. And there are also indications of even older civilizations in South America For example, there is a set of ruins from pre-Incan civilizations on a series of mountaintops, and one of them actually nailed the position of the equator more accurately than the European cartographers that came later. So if you go to Ecuador, there's there's like a park with a big line where the equator is painted, and it's actually a few hundred meters off the actual equator. And these pre-Incan civilizations actually measured it better than the European astronomers did in the 1700s.
So I can't, I don't
Yeah,
understand, or how do they understand the wobble of the earth? It's like something that takes tens of thousands of years. It's like, how would you do that?
yeah.
How would you
Well,
figure that out?
it's unlikely that they understood it in terms of modern ideas, right? Precession of the earth and things like that. But you just see it it creates patterns in the sky, and doing this pattern recognition.
It's
So the
remarkable.
Babylonians had no sense of the earth going around the sun or any of these things, but they were able to do extremely sophisticated calculations because they recognized patterns repeating in the sky. And so their whole concept of what the structure of this was mathematically was very different. But they were still able to recognize these patterns, these very long-term patterns. And
Isn't it
in the
crazy?
case
Like,
of precession of the equinoxes, it's a 22,000 year cycle, right?
yeah. I
Uh,
mean, what haven't we been like relatively the same brain in person for, I don't know, a few 100,000 years or something like that? Or maybe it's a million. I don't know. But the
yeah.
idea is like, hey, guys like
Modern
you,
humans, a few 100,000. Yeah.
yeah, like if you were born 5,000 years ago, so I was like, you're a smart guy. And you're just figuring these things out. There were people
Yeah.
back then who were smart, but they're like, all right, I'm seeing this, and they were
Yeah. I
piecing things
mean,
together.
they were just as smart as any, modern
Yeah,
physicist or cosmologist. They just didn't have, that weight of history of knowledge,
yeah,
that developed over thousands of years of civilization.
so cool.
But they did remarkable things nonetheless. I mean, it was, the Greeks measured the circumference of the Earth very accurately thousands of years ago by looking at the shadow from a stick. You know,
Wow, wow,
uh,
that's amazing, man. Well, it's fun to think about and talk about because it is this infinite discussion about our place and where we've been and where we're going. And I really appreciate you diving in. Is the book you wrote? I know, but it's geared towards anyone.
it's a book intended for the general public.
Yeah.
So it doesn't. There's a couple of spots where it dives into a little bit of the math, but but not very much. And so it's a book that's intended to explain this idea of inflation and the creation of this inflationary multiverse that is aimed at a general audience.
Yeah.
And so it was fun to write because it's really talking about very up to date ideas in cosmology that are still being worked out as we speak. Right. So we don't know all the answers, and there's still a lot of controversy around some of these ideas. And it's intended to give a snapshot of where we are and some of these very modern ideas about the structure of the universe.
We'll put a link to it in the show notes.
Oh, great. Thanks.
Maybe we could just close this. What are you excited about in this field or otherwise? In
What I have
frontier?
been working on lately is the question of so I say inflation is a theory of what happened before the Big Bang, right? So now the Big Bang in these inflationary models is no longer the beginning of the universe, but it's the end of this earlier epoch. So now you ask the question, well, did what happened before the Big Bang, did that have to have a beginning too? Was there an initial singularity, right? So in the standard Big Bang, there's this initial singularity 13.8 billion years ago where all the laws of physics break down. Inflation replaces that with a transition from an earlier period. So the question is, can you get rid of that initial singularity altogether? Can you construct a universe that goes infinitely into the past? And Alan Turing, in a letter to a friend, I love this quote. Alan Turing wrote that science is a differential equation. Religion is a boundary condition, right? So if you have some boundary there, you immediately you're pushed beyond the edge of what you can say scientifically, right? So the question of whether or not inflation allows you to get rid of the initial singularity altogether is an interesting one. And it turns out that if you look carefully at this, the answer appears to be no. That you can push that singularity very, very far back in time. The inflationary multiverse could be unimaginably old, quadrillions, quintillions of years, much older than the few tens of billions that our current universe is. But you can't get rid of it, that it's still out there lurking somewhere in the distant past, that there is some boundary to this, a boundary in time before which something else had to have happened. And the mathematics of this is very beautiful, and it's interesting to ask this question. But so that I've been writing some papers lately about looking at this question of whether or not inflation itself had to have a beginning, and the answer seems to be yes. That period had to come out of something else, and we have even less understanding of what that might have been like.
It's like we need a bigger and bigger collider.
So yeah.
And then we'll know.
Well, there's no way we're going to build a collider big enough to probe these energies, unfortunately. You're going to have to come up with another way. But
you don't say. Yeah. This has been fun. I really appreciate you taking the time.
Thanks, great to talk to you.
And I love it. I hope people check out your book and your world. And there's a couple other podcasts you're on out there, and hopefully there's more.
So thanks very much for having me. It's been a real pleasure talking to you.
Thank you. And do it again sometime.
All right.